Vibrations are sometimes accompanied by a noise. These noises are continuous and are described as a whine or a hum. The other non-vibration related noises can be momentary, like those described as a pop or clunk. Non-vibration related noises also include air leak or gear related noises. The distinction between a vibration and its related noise and other noises is important because it helps determine what tools and techniques you'll use to diagnose the noise. When a noise accompanies a vibration, diagnose the vibration first. The cause of the noise and vibration is likely one and the same. There are vibration analyzer tools at our disposal that quickly detect vibration frequencies. This data is then used to pinpoint the source of the vibration and noise. Other noises, however, present a challenge because they often don't last long enough for a frequency to be detected, or the frequency may not match any of the known originators. There are an entirely different set of tools that we use to diagnose these concerns. Now let's talk a little more about vibrations and how they show up in all areas of the vehicle. This topic will give you the information you need to know when diagnosing vibrations. Vibrations are often noticed in a component that is far removed from where the vibration is generated. This is called telegraphing, and the route the vibration follows is called the transfer path. Let's use our example of a tire with runout. The vibration caused by tire runout is transferred through the steering linkage, up the steering column, to the steering wheel. As you learned earlier, all rotating components have a frequency. This is normal. Some components rotate at faster speeds than others and therefore have higher frequencies. The primary rotating components in a vehicle are the engine, driveline, and wheels and tires. Each of these components has a unique frequency that can be calculated. The specific frequency at any given time of each component depends upon vehicle speed, gear ratio, and tire size. This said, tire and wheel frequencies are generally between 12 to 15 Hz. Driveline frequencies are between 30 to 45 Hz. Engine crankshaft frequencies are similar to driveline frequencies, but engine firing frequencies are much higher and depend upon the number of cylinders in the engine. Engine firing frequencies are typically between 80 to 200 Hz. The latest vibration analyzer tools detect frequencies and then automatically calculate which component is rotating at that frequency. Other vibration analyzers simply display vibration frequencies, and from that point you must calculate which component is rotating with that frequency. We'll discuss those calculations in the Diagnostic Tools lesson. The engine, driveline, and wheels and tires are all considered originators. Because these components are typically rotating, any damage or imbalance can easily cause a vibration or noise concern. We can use our example of the tire with runout. The vibration frequency originates at the tire. It is transferred through the conductors until it reaches the reactor, in this case the steering wheel. The steering wheel is now shaking with the same frequency as the wheel and tire assembly. From the last page, you learned that this frequency would be approximately 12 to 15 Hz. Sometimes to fix a vibration or continuous noise concern, you have to fix the originator. Sometimes you may only need to fix the reactor or the conductor, and sometimes you may have to fix all three. Proper diagnosis requires you to identify the originator, conductor, and reactor to ensure that you correct the root cause of the concern. If you don't identify the components along the transfer path, you could risk a repeat repair. Again, here is a graphic of our three originators: the engine, driveline, and wheels and tires. Wheels and tires rotate at a different speed than either the engine or the drive shaft. Wheel and tire speed or frequency is typically one of the lowest of the rotating components in the vehicle. It is affected by gear ratios in the transmission and the differential or transaxle. Wheel and tire vibrations are directly related to vehicle speed and tend not to be affected by acceleration, coasting, or deceleration. Wheels and tires are a common source of vibration-related concerns. Wheel and tire concerns are often described as high-speed shaking or shimmying and can be felt in the floor pan, in the seat, and/or in the steering wheel. The major reasons for wheel and tire vibration are out-of-balance tires, tire runout, either radial or lateral, and road force variation. Out of balance, wheels and tires are experienced as a shaking in the steering wheel. The shaking occurs at a specific vehicle speed and may occur at more than one speed. Out of balance wheels and tires occur when one area of the wheel and tire is heavier than the rest of the tire. This type of concern is usually resolved by mounting the tire on a balancer and adding weights just opposite the heavy spots. Because wheels rotate and are in constant contact with the road, they are highly susceptible to vibrations caused by excessive runout conditions. The two types of runout are lateral and radial. Lateral runout is the side-to-side movement of the wheel and tire. The tire does not rotate on a true plane and may appear to wobble in a side-to-side manner. This type of runout can be caused by a damaged wheel or tire. Radial runout is an up and down movement of the wheel and tire. The tire does not form a true circle. There is variation between the center of the wheel and tire assembly and the outer tread. It is also caused by a damaged wheel or tire. A tire and wheel with excessive runout will cause steering wheel and dashboard vibrations. Road force variation can cause vibrations similar to wheel and tire assemblies with radial runout. Road force variation is defined as the loaded tire runout multiplied by the spring rate of the tire. The best analogy would be to think of a tire. Due to air pressure and sidewall stiffness, it appears to be supported by a series of springs. These springs have small variations that are normally okay. If one spring is significantly stronger or weaker than the rest, a bump will be felt as the tire rolls. It is easy to determine the frequency in RPM of the engine crankshaft. Just look at the tach or access the RPM PID. The engine RPM is valuable information to have as you track down the source of a vibration because the speed of all rotating components in the vehicle can be calculated based on the current engine RPM. Think of the drive shaft. It's indirectly connected to the engine crankshaft. Depending on the transmission gear, the drive shaft rotates at a specific speed, either faster, slower, or exactly the same as the engine crankshaft. And drive shaft speed has a direct effect on wheel and tire speed. Depending on axle ratios and tire size, the tires rotate at a specific speed that is slower than the drive shaft. So now you see that all of these rotating components are linked. Now that you know how central crankshaft speed is to driveline and wheel and tire speed, let's look at the rotating components that are more closely associated with the engine. There's the crankshaft itself, and the flex plate, the engine accessories, and the natural firing frequency of the engine. Let's first talk about the crankshaft. Crankshaft frequency is fairly intuitive. When we talk about engine RPM, we are referring to the revolutions per minute of the crankshaft. The engine operates anywhere between 500 and 5,000 RPM, and this depends entirely on how fast the crankshaft is rotating. If there is a crankshaft or flex plate imbalance, the frequency of the vibration will match the engine RPM. Sometimes an engine vibration is due to an imbalanced or misaligned engine accessory pulley. These belt-driven engine accessories often produce vibrations at different frequencies than the engine itself. The accessories produce vibrations of different frequencies because the drive ratio created by the different size pulleys cause them to rotate at different speeds. If you're fortunate, your shop will have Vibrate software. That tool will calculate the drive ratios, but you will still need to measure the diameter of each pulley. If you don't have the software, you'll have to figure them out yourself. Let's calculate a few ratios. By the end of this example, you'll know that if you ever need to, you can figure out the frequency of an engine accessory. First, determine the size of the crankshaft pulley. Click on the crankshaft pulley to measure it. Good. The crankshaft pulley is 5 1/4 inches in diameter. In order to continue with the calculation, you have to convert the fraction to a decimal. So 5 1/4 inches becomes 5.25 inches. This is your starting point. Next, measure all of the other accessory pulleys. One at a time, click on each pulley. The generator is one of the smaller pulleys. It's 2 inches. Now we know that the power steering pump is 5 1/2 or 5.5 inches. It looks like the AC compressor pulley is 3.5 or 3.5 inches. Yes, it's important to measure the tensioner. It could cause a vibration too. It's 3 inches in diameter. Good, the water pump pulley is 4 inches in diameter. One column of our chart is filled in, and now you know the real reason we're doing these calculations. We've got a vibration when engine speed is 1600 RPM. Our vibration analyzer tells us that the frequency of the vibration is 2400 RPM. Let's see if any of these pulleys are causing our problem. You need to determine the ratio between each accessory pulley and the crankshaft pulley. Or in other words, how many times will the accessory pulley rotate during one rotation of the crankshaft pulley? Let's start with the generator. It has a 2-inch diameter. Divide 5.25 by 2 to get 2.6. The generator pulley is smaller than the crankshaft pulley. It has to rotate over 2.5 times for every one rotation of the crankshaft pulley. Let's try the power steering pulley. Its diameter is 5.5 inches. It's slightly larger than the crankshaft pulley. Divide 5.25 by 5.5 and get 0.95. The power steering pulley rotates less than one revolution during one rotation of the crankshaft pulley. Here are the rest of the values. Continue to the next page to see how to fill out the last column in the table. The last column you'll fill in is actually the most important column, the engine accessory frequency as measured in RPM. Take the accessory ratio and multiply it by the crankshaft RPM. Start with the generator. It rotated 2.6 times per one revolution of the crankshaft. Multiply 2.6 times the crankshaft speed, which is 1600, to get generator speed. 2.6 times 1600 is 4160. How fast is the AC compressor turning? If you need to have the frequencies in hertz, divide each RPM frequency by 60. If you're using a tool that doesn't do the calculations for you, you now know how to look at a vibration frequency in RPM or hertz and figure out which accessory pulley is the source of the concern. Engine firing frequency is the last engine-related vibration that we'll talk about. Engines have vibrations created by firing frequency. Firing frequency refers to the force created by the engine each time a cylinder fires. The force of combustion creates one pulse, and the cylinders firing in order create a normal vibration. The frequency of these vibrations is dependent on the number of cylinders in the engine. For example, a 6-cylinder engine fires half of its cylinders with each crankshaft revolution. This results in a third-order vibration because there are 3 disturbances per one crankshaft revolution. A fourth-order vibration would be common with an 8-cylinder engine, since 4 cylinders fire with each crankshaft revolution. The firing frequency is engine RPM times half the number of engine cylinders. The higher frequency lets you know that the vibration may be second, third, or even fourth order. Here's an example. Let's say you're test driving an 8-cylinder. When engine speed gets to 2400 RPM, you feel a vibration. The vibration analyzer tells you the frequency of the vibration is 9600 RPM, or 160 Hertz. That's a pretty high frequency, so it's likely that it's second, third, or fourth order. Let's do a quick calculation to see if it matches engine firing frequency. The vibration was felt at 2400 RPM, so let's plug that into our equation. Now we need to multiply that by half the number of cylinders. So 2400 should be multiplied by what number? Yes, you should multiply 2400 by 4 to get a firing frequency of 9600 RPM. Now you've found the source of the problem. The vibration you felt at 2400 RPM is the same as firing frequency. The fix to this vibration may be a worn or damaged engine mount that is not functioning properly, since it's failing to prevent this engine vibration from reaching the passenger compartment. The driveline is the system that transfers all the rotational torque from the engine and transmission to the wheels and tires. It consists of the drive shaft, CV joint, U-joint, differential, and rear axle. The drive shaft is the largest of the driveline's rotating components and is a common cause of vibrations. The drive shaft has its own unique frequency that is typically different from the engine and wheels and tires. The exact frequency of the drive shaft depends upon engine speed and gear ratios. Drive shaft speed matches engine speed only in direct drive. At all other times, drive shaft speed is modified by gear ratios in the transmission. Likewise, gear ratios in the axle modify rotational speed, causing the tires and drive shaft to rotate at different speeds. The driveline can be the originator of a number of vibration concerns. These concerns are typically felt through the floor or heard as a rumble, hum, or boom. There are two types of driveline-related vibration concerns, those that are speed-related and those that are torque-related. We've talked a lot about the speed-related concerns. These vibrations and noises are evident to the driver only at specific vehicle speeds. They are typically due to an out-of-balance drive shaft. A damaged drive shaft, wrong or missing weights, or wrong U-joints can all cause an out-of-balance drive shaft. The second type of concern is torque-related. Torque-related concerns occur at lower speeds, typically during acceleration after a stop. When the drive shaft is under more stress, components like worn U-joint bearings or incorrect driveline angles have a tendency to cause noise and vibration. An imbalanced drive shaft is a common cause of vehicle speed-related vibrations. As the drive shaft rotates, the heaviest area on the drive shaft is a disturbance that causes a tremor or vibration felt in the seat or floor pan. Causes of the imbalance may include wrong or missing weights, damaged drive shaft, wrong U-joints. A vibration caused by wrong or missing weights can typically be resolved by adding weights to counteract the heavy spot. If the drive shaft is damaged, it cannot be repaired. It must be replaced. Be sure that the correct U-joints are installed on the vehicle. Drive shaft runout can also cause speed-related vibration concerns. A drive shaft with runout rotates outside of its intended plane. The rotation of the drive shaft is not truly round and appears to wobble. A bent drive shaft, worn U-joints, or a bent pinion flange can cause drive shaft runout. To understand torque-related vibrations, you need to first understand the driveline working angle. Any connection made with a U-joint can create an angle. In this example, there is an angle between the transmission output shaft and the drive shaft. There is also an angle between the drive shaft and the pinion shaft. Because of the first angle, the transmission output shaft and the drive shaft do not turn at the same speed. As the output shaft rotates, the drive shaft speeds up and slows down. You now know that the transmission output shaft and drive shaft do not turn at the same speed. Because of the second U-joint, the drive shaft and pinion shaft don't turn at the same speed either. If each angle is roughly the same, they cancel each other out, and the transmission output shaft speed is very close to the pinion shaft speed. The angles are most exaggerated during a torque or load condition. When under load, the rear axle flexes or moves, changing the angle between itself and the drive shaft. When the working driveline angle is within specification, this amount of movement doesn't affect the operation of the vehicle. However, if the angles are not within specification, this movement causes a vibration as the drive shaft rotates. You can feel the vibration in the seat and the floor. Load conditions have a way of amplifying the effects of a worn or binding U-joint. Under normal conditions, the U-joint doesn't cause vibration concerns, but when the U-joint is stressed by the increased angle, it binds and causes a vibration. Up to this point, our focus has been on originators, but other components along the transfer path may vibrate. Now let's look at some of those components that could result in a customer concern. Sometimes you'll need to repair a conductor or reactor, and sometimes you won't. The important thing to determine is whether you've identified the root cause of the vibration. A vibration and noise transfer path includes a wide array of vehicle components, including body mounts and bushings, sheet metal and body welds, as well as the steering linkages described earlier. Sometimes the reactor is not interior to the passenger compartment, but instead is an exhaust heat shield. Now we'll take a look at the components designed to prevent vibration. Vehicles are designed to prevent vibrations from reaching the passenger compartment. Mounts, bushings, and isolators work to dampen vibration. If these components fail or are installed incorrectly, vibration is allowed to travel along the transfer path. So you should look for damaged mounts and bushings during diagnosis. Rubber or plastic absorbs and dissipates the vibration before it causes a concern. Vibration dampers are also used to prevent vibrations, but the way they prevent vibration is different. Dampers are weights added to a component in order to change its resonant frequency. This prevents the component from shaking when the engine, driveline, or wheel and tire frequency reaches its resonant frequency. This topic covers other types of noises that we don't think of as being related to vibration concerns. These noises include the momentary pops and clunks associated with worn or damaged components, the grinding noise associated with gear-driven components, and wind noise or air leaks. Many times these concerns are identified with a visual inspection. Now our graphic depicts the components or systems that could be responsible for causing noises. The graphic includes the vehicle's body, steering system, suspension, brakes, driveline, and engine accessories. The suspension system is a common cause of vehicle noises. Control arm bushings, springs, shocks, and struts are all susceptible to wear, which can result in noise. A shock or McPherson strut can cause noise due to internal damage or improperly torqued mounting hardware. Leaf springs can cause noise if they come in contact with each other or have a missing leaf tip insulator. On coil springs, a damaged or missing isolator can also cause noise. Bushings can cause noise if they're worn, deteriorated, or contaminated. Noise can also be caused when an outer or inner bushing sleeve tears loose from the rubber and rotates. Steering gear, tie rod ends, and ball joints are mechanical components subject to a great deal of wear. The linkage components can cause noise if they are loose, binding, or seized. The steering gear could cause noise if the gears are worn or improperly lubricated. Noises from engine accessories can be caused by belts that are incorrectly installed, contaminated, incorrectly adjusted, worn, or glazed. An engine accessory with a defective bearing, pulley, or gear may also cause noise. Be sure to thoroughly inspect all engine accessories when diagnosing the root cause of a noise concern. Loose bolts, broken pinch welds, and damaged body mounts can all cause body-related noise, such as rattles or clunks. Inspect for damaged or improperly torqued components. A momentary clunking noise from the rear of the vehicle during acceleration could be caused by worn U-joints. Excessive rear differential backlash could also cause a clunking sound, especially when shifting from reverse to drive. A howl or whine could be caused by gear damage in the differential. A squeal, grinding, or thumping noise may all be attributed to the brake system. Squealing may occur when the disc pads or brake shoes contact the rotors or drums. The noise may go away after a few brake applications. If not, check for excessive brake pad or shoe wear. The thumping noise could be caused by brake rotor or drum runout. Other noises are produced by wind, turbulence, and air leaks. Wind noises are caused by air escaping from the vehicle. Turbulence is air moving over or around loose or protruding moldings or between gaps in rubber seals, moldings, and drip rails. You may need to seal areas from which air escapes the vehicle or secure loose or protruding components.